Tight oil, compared to conventional crude, has been shown to contain more metal contaminants, which have been shown to cause many issues, such as fouling and catalyst deactivation. Metal contaminants that are commonly found in tight oil include alkali metals, such as sodium, which happens to be the most prevalent metal contaminant in Bakken and Eagle Ford, arsenic, iron in trace amounts, mercury, nickel, and vanadium. Both nickel and vanadium are found in asphaltenes. The following table compares the amount of common metal contaminants in Bakken and Eagle Ford tight oil. The high paraffin content of tight oil creates issues when blending with asphaltenic crudes. The mixing of highly paraffinic tight oil with asphaltenic crudes causes asphaltene instability and leads to crude incompatibility. Crude incompatibility can lead to decreased energy efficiency, increased carbon dioxide emissions, the need for heat exchangers to be cleaned more frequently, and decreased throughput. To avoid asphaltene precipitation problems, tight oil should be blended with heavy crudes with an API gravity of 13 to 16 degrees API to yield a blend of 21 to 23 degrees API. Here is our sponsor's experience. The Asphaltene Stability Index Test, or ASIT, from Baker Hughes, a GE company, is a tool for determining asphaltene stability of crudes and crude blends. Field ASIT Services technology uses a portable automated titration device using near-infrared laser to detect onset of asphaltene flocculation. The testing can be routinely performed in the refinery. The ASIT plot is the normalized laser power intensity, on the y-axis, versus the asphaltene stability index or ASI, on the x-axis. The curve inflection point is the asphaltene flocculation onset and ASI value for the test. In the chart depicted, the black curve represents the base crude for the refinery with a moderately stable ASI value. The blue curve is an opportunity tight oil with no well-defined flock point. Additional information is required to define the ASI value of this type of crude. The red curve is the targeted blend of base crude and opportunity crude, demonstrating a very unstable crude blend that will require problem mitigation. Blend asphaltene stability information can be used to help guide crude selection, blend ratio decisions, and problem mitigation planning to manage risk and maximize refinery profit. Data obtained using the Field ASIT Services technology can be coupled with the BHGE crude compatibility model to further evaluate blend stability for new and proposed blends. The BHGE crude compatibility model is a proprietary mathematical model that can estimate the ASI of a crude blend based upon the ASI values of the individual crudes and some additional crude characteristic values. The example plots depicted are simple two crude blends. The blue data represents the model calculated ASI value on the y-axis versus the blend percentage on the x-axis, 0 to 100%, of one of the crudes in the blend. ASI measurements of physical blends are also plotted validating the model values. Blends containing as many as 8 different crudes have been modeled and lab test validated in a similar manner. The values used in the crude compatibility model can also identify the theoretically defined incompatibility points for various crude oil blends. These would be blends that potentially should be avoided, or more extreme mitigation efforts required. A crude oil database can be developed to facilitate planning of how a new crude, or a new crude blend, may impact the refiner's operation with respect to asphaltene stability. The model also facilitates ASI quantification of various crudes that do not produce a well-defined flock point. How these no-flock crudes behave in the blend is of strong interest, as many of these crudes induce asphaltene instability.